we directly move on with the next keynote. The next keynote is being presented by Professor Antonio Krüger. He's the CEO of the German Research Center for AI and head of the Department for Cognitive Assistance. And he's presenting his vision or his view on useful AI, potential and development of AI methods within the DFKI ecosystem. The stage is...
Do I have a... Yeah, thank you very much. I would like to thank the organizers that have brought this conference together, because as we've heard earlier, it's important. We are in a critical point in time, and we need to join forces in Germany, but also in the European Union, to be part actually of this fantastic development that is currently taking place. And to also harvest the potential and mitigate actually the risks that are related to AI. I would like to discuss with you, to present to you some views that we at the German Research Center for AI have on how AI technology and in which areas it will be in particular useful in the future. And I use this term useful AI a little bit, maybe ironically, because AI has been useful so far. Also, and it has been mentioned by Thomas Saueressig, that AI, there has been long-term research, there have been achievements. AI has been under the hood of many technologies, from navigation systems to consultancy software and so on. But of course, what we witness now is kind of an uplift and a further acceleration actually of the potential of AI. So there has been, in the last kind of 60 years, there has been always kind of a mix of AI techniques and a focus of research on different types actually of aspects of AI. And in the last 10 years, this kind of eternal pendulum of AI methods has clearly moved towards actually numerical and statistical methods, in particular related to machine learning, in particular, of course, related to deep learning. Yeah? And we've seen in the previous presentation, you know, the ingredients that have really uplifted the technology, and of course, the possibility to use large language models, dialogue models, to try this out by yourself have led actually to a broad awareness on all levels in society. And other than maybe in past decades, where we always had kind of like a AI summer, and that was basically followed more or less by an AI winter, because the hype expectations, you know, were not met. We are now, that's something I strongly believe, we are now at the beginning of a phase of a long kind of uprise of AI techniques, and that will basically permeate all types of software, as we've heard before, all types of systems. What is interesting now is the question how to integrate AI into our society. And this, you cannot take just a neural network, you know, that you've trained and then put it to use. You need to integrate it. You need to integrate it into processes. You need to understand, you know, what a particular AI system or piece of AI technology can do, and how it kind of communicates and how it corresponds to actually the context of its use. And that is what we at DFKI termed systems AI. So you need to understand how AI has to be integrated into existing system, into new system, into kind of an orchestration of different pieces of technology. And this integrative AI, this is actually the AI that is useful. And this is something where we still are at the beginning to have, in research, fundamental understanding, you know, how to do this. If you think about software development, you know, in the early days, if you compare this in the early days, let's say in the 80s, and how software development has been done, let's say, in the last 10 years, you know, the understanding of how software engineering works, you know, has fundamentally changed actually the productivity, the reliability, and the safety of software systems. And something similar we need to achieve also, of course, for AI systems, because this is crucial. We know that in particular, and it has been mentioned, the hallucinations, but also other kind of lack of explainability, lack of inspectability. So if something goes wrong, then how can you make sure that the next generation of the system does not make the same mistakes? Yeah? How can you debug such systems? Yeah? If you think about, a good example is aviation. If you look at history of aviation, of course, aviation is inherently risky, but through the ability to inspect inspection and then being able to improve the systems, flying is now one of the safest way to travel. And something similar we need to achieve for AI, so that AI systems really basically are in the end systems that we trust. And this then, of course, will lead to a whole new kind of, I would say, mix of AI systems. What we also have to keep in mind, how to do this technologically. And as I said, it will be very likely a combination of methods. At the core, there will be very strong, very well trained, on lots of data trained neural network approaches. But around those, we will have lots of other kind of knowledge-based systems that rely on knowledge that is established, that we know, and that basically helps to safeguard actually the output of systems that purely rely, or parts of the systems that rely on statistical methods. This is one way actually to achieve kind of systems that are explainable, that are inspectable, and then are also trusted systems. We've also heard, this is also an important research direction at the moment, is that we need to rethink how humans interact with systems. While if we look at classical interaction of humans with software systems, then those are more control-based. If you think about your graphical user interface, where you have a mouse, where you can basically control stuff and do things and so on. So this will move much more to oversight. Yeah? And again, if you look at aviation, also in aviation, a pilot of a large commercial aircraft, he's not directly controlling usually the airplane. Basically, the pilot, he or she, they are basically having an oversight. They're overseeing a complex operation. And of course, in certain situations, they need to be able to take over and to control on a more finer-grained level the system. And something similar will happen actually with complex AI systems. So humans will rather oversee the operations. We've seen this a little bit on the dashboard in the earlier example. But then, if necessary, they need to be able to drill down. This means also that for fundamental tasks and workflows, the knowledge how behind those workflows need to be still there. They might be not executed as often, that knowledge, as before, but we need to have this. And this, again, is interesting because it leads to kind of a different type of education, different type of skill set that somebody might needs to have. And then, of course, fundamentally different type of interfaces if we integrate human intelligence with artificial intelligence. So there are the next generation AI systems. Here are a couple of examples. What we will see much more, and I will talk a little bit, give you some examples in the remainder of the talk. What we will see for sure is are much more self-learning systems that exhibit also higher degree of autonomy as so far. So this is something. Some of you might have a vacuum robot, that kind of is able to autonomously run through your apartment and basically basically clean actually the floor. Of course, this will be expanded. It's very likely, that foundation model, large language models, but in general, AI will help to provide systems that are even more complex, can do more complex tasks, in environments that are not well known. But the interesting part is the fourth part here, are hybrid human and AI systems. So, for example, robots that work together with humans in teams, so not only maybe one-to-one, but kind of more complex situations. And these kind of systems, they, of course, have an even higher requirement for safety, for reliability, for robustness. And this, again, will be very likely achieved by having hybrid systems that, for example, take well-established knowledge that we have, for example, through physical models. If you think about modeling basic physical properties through differential equations, makes no sense actually to take these very solid physical models that are a very good description of the world and replace them, for example, by a machine learning component that learns the same thing, but then has an output, that is not as reliable, actually, as a physical model. That's what we call neuro-explicit models. So you have a neural part, a neural net that does most of the work, but then you have an explicit part that acts as a safeguard and complements, actually, the situations where the statistical model is more error-prone. Same example in car driving. No autonomous car manufacturer or supplier would think about having actually the traffic rules and traffic codes actually learned by scratch. You can in generally do it, and they're as good as humans, but we know how good humans are to basically follow actually traffic rules, so and regulations. So those things will for sure be modeled explicitly. This is important because also for legal reasons you need to make sure that these things are basically regarded. And other things like keeping the car on the road, like identifying signs, identifying even flowing traffic and other traffic participants and so on, those tasks, of course, are inherently carried out then by machine learning, by deep learning approaches, and so on. And how to integrate these things, Currently, we are in an early phase of experimentation. So there are no clear kind of design guidelines, rules, how to do this. So in all areas, as said, of society, exploration takes place at the moment. So combination, machine learning, and knowledge-based methods. And one, of course, very important model here are foundation models. We've heard about those. Those are, of course, not only large language models, but inherently more. We see already GPT-4, for example, but also BART have also the Lambda and also the other models are already trained also with multimodal data. This is a next step. This is increasing actually the semantic representation that these models provide about the real world, and we expect actually, we don't know, but we expect that actually the output will be more robust and better. There's this interesting observation that that in a way, computer science has always been a discipline, from that has a strong design component where output was pretty reliably predictable and with a very clear way how to debug stuff. This has changed, of course, with the large networks, with large neural networks. It's much harder to predict, what happens if you increase the amount of parameters, for example. So if you look at how these parameters have been increased, and how much the computational power that you need basically for large networks, that you need to basically compute those models. For the large language models, for example, there have been full Microsoft Azure farms, server farms, actually, that was 3 months and more, doing nothing else than computing these models. And of course, you want to know what you get, if you scale up Yeah? You want to know, is it worthwhile the investment? And to be honest, I'm very grateful actually for companies like OpenAI that took the bet, invested $1 billion actually to try out. But it was unclear in the beginning if this would work. And why the scaling work, again, this is also the truth, is also not 100% clear. Yeah? And whether, if we continue to scale, whether this will fundamentally change the way how these systems work, we have no idea. Of course, people will try, so we will see this in the next years, decades. There will be people willing to take the bet. But from a research point of view, we don't know. Yeah? So we will see. Again, this is, we are in a similar situation as, for example, 150 years ago, when the steam engine has been invented, without knowing nothing about thermodynamics. So the laws of thermodynamics, they were unknown at that point. Still, of course, you could operate a steam engine, and you could scale it up, and then it would blow up at a certain point in time. Yeah? And, but of course, only kind of understanding research and the physical laws tell you, the boundaries in a way. You can predict things, outcome. And we are currently in a moment where we try to find out, to understand these rules. And sure, yeah. At the same time, these are the figures actually that also Thomas mentioned. At the same time, the investment, it's always the question, is the investment worth the money? Yeah? And can we operate them safely? Can we even find systems that don't use actually so many parameters and have the same output? Yeah? So reduce the parameters, which at the same time would also reduce the CO2 footprint of these systems. So that's also a very important research directive that current international research is looking at. The question about data is also very, very important. For many language models, for example, and foundational models, we have no clear idea with which data these models have been trained. We have a rough idea, but we don't have a clear idea. This again, is something that I believe is at least something we should think about, and it would help actually if we would know exactly, with what kind of data these models have been trained. Yeah. Of course, you can safeguard later on through prompt engineering and meta prompts and so on. You can safeguard somehow the output, but of course, the bias and the influence is within the data. And of course, most of these large models have so far been trained with data that is more or less freely available. Of course, there are some lawsuits going on copyright infringement and so on. But again, this data is usually not of very good quality. So there's lots of noise in the data, which again kind of affects system performance. If we would train, for example, a foundational model on high quality data only, like for example using video material from BBC, I'll just give you an example. It's pretty good curated, high quality data, plus actually all kind of high quality text and other kind of and images and so on. We have no clear idea how actually the output of these foundational models would change. What we know for sure is foundational models will have a large impact on all kinds of applications. For example, in robotics. Yeah? Robotics lacked so far often from a good understanding of the world, from the semantics of the world. So having a robot that can orient itself in an arbitrary environment is not easy. Has never been an easy task. And now we have the chance through the semantics of the foundation model about how the world works and so on to basically make big leaps forward. So in all kind of applications, we at DFKI, we are kind of trying to explore this area, to work there. We have a very strong, and this is important because it needs a high degree of autonomous robots, a very strong track record in space robotics. and also in underwater robotics. Those are two areas where robots basically can only in a limited way be teleoperated. You know, if you think about rovers on Mars, those are very hard actually to operate. Yeah. So this is one way where I believe, you know, these models will make a big difference. And of course, in human-robot collaboration and cobots. This has the big advantage that in that area, we have a very good worldwide standing in Europe and also in Germany. We have very good companies, very competitive companies that are clearly absolutely on par to American and also Chinese companies. And we have a track record, you know, in developing these systems also with industry. And when I talk about robots, it's not only physical robots or robot arms, it can be also soft bots, so actually avatars that provide assistance over a screen or over an embodiment. It can be robots that have special tasks, you know, and work in a team, like here, a project together with Airbus, that where we work together, and that help, for example, to support human workers to reduce actually the strain of certain tasks, like overhead mounting of certain elements in an Airbus, so-called raceways. That's what we tried out here, and these kind of systems we'll see more and more, because large foundational models also help to bridge actually the understanding of the robot on what humans are able to do. This is also very important, and to also judge how humans will react to certain actions that they do. Currently, this is tricky, and therefore often robots that interact actually with humans are super slow, much slower than humans themselves, and you see here also examples. But this is something where I also believe this will change significantly. And I would like to finish my talk with one topic that relates also to the other symposium, the quantum computing symposium, and this is quantum AI. There also I see enormous potential, mainly because problems in AI are very hard, require lots of computational power, and quantum computing provides means to overcome that barrier. And in fact, if you look at the area of machine learning, which is the very prominent part of AI, then even on the data side, so you can have different kind of approaches. You can have classically use normal data and apply quantum computing methods, but you can also have data represented by qubits, so by a quantum approach, and use actually quantum computing approaches. And here we are currently again in an exploration mode. We are currently understanding what kind of problems can be solved and which problems cannot be solved. Because it's not like you can take a quantum computer and just apply it to AI problems. You need to rethink, and certain problems will very likely not be able, we will not be able to solve them with a quantum computer. Okay, so here you have these different patterns. On the left, the data, quantum and classical, and the type of algorithm, which is classical and quantum, and you can have all kind of combination. And of course, the goal is to use quantum data with a quantum computing approach. And with that, I would like to thank you for your attention, and I'm open for questions. Thank you very much.
Thanks a lot, Antonio, for your insights. So one general question when it comes to the ecosystem in Germany and the knowledge transfer. We discuss it a lot with policymakers. So how can we get all the innovations you think through in a relatively early stage from when it comes to application? How can we get it better to really application in the broad economy?
Yeah. So I believe the key here is, especially for Germany and also for Europe, to enable the small and medium enterprise companies to adopt AI technologies relatively fast in their products. We have this enormous wealth and also the ecosystem of these hidden champions, for example, and they need, most of them will very likely have to integrate AI to also be top-notch, actually, in the next 10, 20 years. And I think we need to make sure that we be able to transfer this. SAP, of course, as somebody who provides tools for businesses, are also, of course, key players, but they are also smaller companies, you know, that might not even be able to afford an own AI department or even kind of a very costly AI software. And this, I think, will be critical in a way. At least for Germany and Europe.
Thank you. So I totally agree with you. With all the SMEs in Germany, it's very important that they stay competitive with AI.
Absolutely.
Thank you, Antonio, for your presentation.
Thank you very much for having me. Thank you.